Okay, good morning. We're about to start. Michael, if you could put up the first slide, please. Right, we've decided to try and confuse you before we've even started. So this is not session 3. We've just found out that our first slide is incorrect. This is actually session 4. So you are not going to be presenting on the use of the 4.0 platform. We had that last week. This presentation is on passive house principles. So I apologize. So it's passive house principles and approach. And I apologize for the first slide being wrong. Barry McCarron will be doing the presentation today, which is about 30 minutes long. He's one of our project partners from Southwest College, and I'll introduce him in a minute. Next slide, please, Michael. Okay, usual rules. If you could switch off your microphones while the presentations are being made, switch off your cameras when you're not speaking, though you can switch your camera on later on when we get to the questions and answers. You can ask questions as we go along in the chat group, and I would encourage you to do it as we go. So don't save questions up to the end because you'll forget what you're going to answer. We'll try and get through all of the questions if we can. We had one session 2, we had so many questions that we overran by 10 minutes. I will try not to allow that to happen today. To remind you, we're recording the presentation, but once the presentations are over, we will switch off the recording so that nobody feels inhibited about how they discuss openly when we get to the question and answer session. And Colin will give feedback to anybody. So if there's anything that needs to be addressed after the presentations are finished and after we're finished today, if you could get back to Colin or to Michael Dean, and they'll answer your questions. Next slide, please. I think most of you, again, I'm looking at who the participants are today. Most of you have been through all of this before, so I'm going to run through this very quickly. What the presentation today is from Barry McCarron is basically on the low operational carbon approach. So this is passive house principles and how to approach that for stakeholders. Next slide, please. Barry is the acting head of business development. He's recently got his PhD. He's very intelligent. I've been working with Barry for about 10 or 12 years, mostly in Northern Ireland. He has a very good reputation, both as a researcher and as a presenter. And I think you'll find his presentation very entertaining today and very clear and concise. Next slide, please. Run through this very quickly. I'm only going to take about 3 or 4 minutes on this. This obviously is part of the H4.0 project, which is an Interreg Northwest Europe housing project. What we're trying to do is to develop new solutions for small, affordable, low carbon and energy efficient homes. We do this by using digital technologies, using low carbon materials and construction methods. So one of the things that we've talked about a lot before is over the last 5 or 10 years, there's been a lot of focus on energy efficiency once the house has been constructed. But what we're also looking at within this project is low embedded carbon. So this is how much carbon is going into the materials from which the house is constructed. Next slide, please, Michael. Again, as you know, we've got 8 or 9 partners within this. You can see down 4 from the bottom. SWC is Southwest College, and they're based up in Omagh, and they're our partner who are doing the presentation today from Barry. Next slide, please. 3CEA's responsibility was to develop 4 social housing projects in 3 counties. For various reasons, the Wexford site will not be going ahead, but Carlow and Kilkenny have started on site. I have to say for the councils, this has been quite onerous because we're changing the way that they would normally deliver. They've been very helpful and supportive in trying to adopt new solutions, but they've always been fighting against the status quo, not against the state, but against the status quo to try and find innovative solutions. What we're trying to do with an H4.0 is to have a 60% saving of carbon emissions and also a 25% cost saving in the long term, not necessarily within the project, once this benchmark has been implemented. Next slide, please, Michael. Okay, the objectives. We're looking at NZEB, and also today Barry will be talking about Passive House. So he will also highlight the difference between NZEB and Passive House. We're talking about the platform. We had a presentation on this last week about planning, designing, manufacturing and assembling units. And also we've already had a presentation on wooden materials and technologies. And then later on, we'll be talking about business models and implementation, but that's not for today. Next slide, please. Okay, you'll be glad to hear this is me just about to finish. These are, again, the objectives of H4.0. As I've said, we're looking at both operational and embodied CO2. We're looking at the Passive House approach for operational CO2 emissions, but we're also looking at the low carbon first fabric approach. So this is, what are you putting into the building and what is its carbon footprint? So you'll be glad to hear that's the end of me. I'm now going to hand over to Barry. Barry will be talking for about 30 minutes, and then we'll take questions and answers afterwards. Barry, the floor is yours.
Thank you, Michael, and thanks for the warm introduction. It's really nice to be working with Michael, and as he said, many years of working together, particularly here in Northern Ireland. So this is my presentation, and hopefully I'm able to generate lots of thinking so that at the end we have a really strong question and answer session and discussion, hopefully, as well. So I'll go light on the first few slides. As was outlined, we've multiple partners in this Interreg Northwest Europe project called Housing 4.0. So again, we'll not limit that. Of course, for everyone here, it's no surprise that you know, it's incumbent upon the construction industry to really get to grips with everything to do with the climate change imperative. And when you consider that 40% of all emissions roughly come from buildings, be it operational carbon and embodied carbon, then it really is what you could say low-hanging fruit for a government or intergovernmental approach to solving the situation we find ourselves in. And then this slide here is very interesting as well, and it's relevant to the whole topic of indoor air quality as well. So you can see here from 1750 all the way to 2010 in this graph, and in recent years right up to 2019, we're looking at the CO2 parts per million outside going across 400. So you will have seen in the news over the last years with COVID and the pandemic, a lot of talk about monitoring CO2 in classrooms in particular, but also a renewed consciousness around indoor air quality. And what's really unfortunate when you get into the classifications of indoor air quality 1 is less than 400. So it's actually a fact that outside we no longer even have indoor air quality 1. We can you know, filter rooms and bring it back to that you know, lower level of CO2, but outside globally the CO2 levels across 400. So I think that's stark and an interesting way to start the discussion. And I'm actually presenting here from the Southwest College Earn campus building, and I'd encourage you to look it up. And we've been monitoring this building from it was opened, which was in September. So we have October, November and December, and now January's data. And the buildings, the whole internal average CO2 is just sitting at 470. So we've excellent indoor air quality in this building to date, and it's a certified passive house building, which is much of what I'm going to talk about later on. Well, and now I've went ahead of my slide. So as I was saying earlier, you know, 40%, and this figure fluctuates at the moment. Different presenters are saying different things, but it's roughly around 40% of the CO2 is coming from energy going into buildings. So this is why there's a big focus and emphasis on this at the moment. So again, when we're looking at NZEB, it's very closely related to the Passive House standard. In many ways, the building blocks of NZEB, as it was designed as an EU directive, actually come from downstream from the Passive House standard. The Passive House standard has the metric of 15 kilowatt hours per meter squared of floor area in any building. What it does not include, the secret's in the wording of it, I hope that's not too patronizing, is the heating demand. It does not include the heating demand for hot water. So if you tag onto it the domestic hot water or the hot water demand for any building, which is rule of thumb around 30 kilowatt hours, that's double the 15 actually. That just shows you how low Passive House is. Then that gives you this golden figure of 45, and guess what? The NZEB figure is 45. So when you include hot water and the heating demand, it's more or less encouraging you to go with the Passive House standard as an enabler to achieve NZEB. And what I really like about it from my point of view is it adds another quality assurance framework around the design and build process. So that's what I'm saying in that slide. So how does this Passive House standard work, and how does what the approach that I would recommend to near zero energy buildings really consist of? Well, the global campaign from the International Passive House for this last year was, energy efficiency is the first renewable. So in other words, or in Irish terms, don't put the cart before the horse is another thing that's been said. So really how that works is it's really about employing 5 principles. And these 5 principles are really, in many ways, when approaching this standard, not really up for debate, because if you drop one of these principles out, you could in turn then be locking in a problem. And I think, for us in Ireland and the recent history maybe with, problems with buildings, it's really important we get this right from this point on. We do not need to have another issue later on down the track. So a lot of what I'm talking to them, I'm very passionate about avoiding the trouble. And I think these 5 principles really hit at how you have a good high performance building that is quality assured. So the first principle in any passive house is high levels of insulation. And in the Republic of Ireland in particular, this is really good news, because our building regulations, when it comes to thermal performance of the floors, walls and roofs, we're almost at passive, all but there. We have really, so cost differential doesn't really come into it, or product selection doesn't really come into this. It's just about getting to the 0.15 U value. So when you have those levels of insulation, what's really important, what the second, it's in the wrong order here on the screen, but the one that goes hand in hand with insulation is the thermal bridging. So if that's basically the floors, the walls, and the roof junctions where each of them meet, and also where the windows obviously penetrate the walls, it's at these situations where you want to make sure that you've got a good enhanced detail, and that it's been assessed to make sure that there's no fear of condensation or mold. Thankfully, that shouldn't really be happening now anyway. But also as well, when modeling this in the building physics, it's really important that the surface temperature doesn't go any lower than 4 degrees from the design temperature of the room, which is considered to be 20 degrees. So we really need a surface temperature no lower than 16. And the passive house process has that baked in already. So that's the thermal bridging. The third one is almost standalone, and that is triple glazed windows. And you're really trying to, perhaps some people, have it in their head that we should optimize the building to face south. Not so much. It's really actually about reducing the windows on the north side of the building for where we are globally in Ireland and the UK, because north facing windows, particularly if there's a lot of it, is just a draw on the building the whole time. So triple glazed windows is the third principle. And then very quickly, very easily, the fourth and fifth ones are you make a building airtight, and there's no reason to be fearful of making a building airtight because you're mechanically ventilating. So it's exactly a nice little analogy here, you know, that sums it all up, is our car. I was coming here today, the set point actually in the car, very interestingly, is at 21 degrees. And if you go to turn it up, it cuts out, and the word high comes up after 25 degrees, which is the metric for overheating. And then if you were to turn it down, actually in the car as well, it cuts out at 16 degrees and says low. And 16 degrees is what's considered the comfort criteria. So all these things are already understood in science and other places as well. So it's not any different with buildings. So the air tightness and the mechanical ventilation go hand in hand. That's the key. So anything else in that makeup, if you have a particularly airtight building and you are not going mechanically ventilated, that's a recipe for trouble. Or equally, if you're putting in a mechanical ventilation unit and the building is not particularly airtight, you're going to get trouble. And another area of trouble sometimes is also around this thermal bridging issue as well. So again, I spent a bit of time on that slide, but I think it's a very important one, and look forward to discussion on that later on. So again, this sort of just reiterates a little bit of what I was saying, and it's no harm to just go over it again. So, I mean, the high levels of insulation, and I talked about this, and the U value that you're aiming for is about 0.15. Now, what's really interesting when talking about that insulation, that's not a prerequisite. You can have U values outside of that 0.15, and that's what's really good about these standards. You can make it up elsewhere. It's not as hard and as fast and as rigid as people believe it is when it comes to that. So the thermal insulation is the first principle. Passive house windows, I talked about again. The recommendation here is to have the windows at a U value of 0.08 after they're installed. But typically, if you get a good quality triple glazed window and you install it correctly, this shouldn't be a problem achieving that. The third, or the order is a little bit messed up here, but the order, or the mechanical ventilation unit, these are all really sophisticated units now, and our marketplace and supply chain is more than able to deliver this to the marketplace. We have one of the prerequisites for these types of ventilation units is that they would have an efficiency above 75% heat recovery. So again, for anybody who's not familiar, it draws air from some of the warm rooms in the house, some of the wet rooms where there's perhaps stale air, and those rooms are typically have a lot of heat in them, and the heat exchanger will hold that air, that outgoing air, the heat out of it, and at the very same time the incoming air gets heated by the outgoing air through the heat exchanger. And on both sides of this, it's filtered, so you're getting nice clean air as well. And I've already talked about the CO2 thing as well. So it's quite common to have your indoor air quality level in a passive house sitting at around 600, 800 CO2, even with the occupancy of the house in all the various rooms, and that is excellent because it's not over the critical figure of 1,000. The air tightness we talked about very briefly there again, but just to say about it, the standard for passive house is 0.6. It's actually not as hard as people think to make buildings airtight. Typically, you know, all I would say at a high level about it is that if your construction is masonry, then a lot of your air tightness barrier will be plaster. So it's a very cheap product. It's getting done on site anyway. You just have to have a little bit more thought about the sequence of what goes where and when it goes. And moving on then to timber buildings, typically where there's timber in a building or a timber frame building, then you're really using tapes and membranes in many situations there as well. So that's air tightness. And then the last one again is the thermal bridge. And I talked about some of the science around that. Typically we want these details to have no surface temperature lower than 16. And again, over the last 3 years or more, the amount of people who are able to thermally assess models, the amount of practices that have this in-house, maybe not to accreditation level, but have the capability to do it, is increasing all the time. So the construction industry really is on track to meeting these standards as well in many ways. So again, this just sort of shows an overview of this, and again, it's a recording, so you'll be able to look this back after the presentation. And what you have here is actually a really good slide. While it says on the slide that it's the German standard back in 2014, that actually mimics the Northern Ireland situation at the moment, and the typical U values that exist in Northern Ireland for buildings, and beside it you have the passive house levels. So the Republic of Ireland is somewhere in between, or well, actually very, very close to passive house as it goes, and the thicknesses are very similar there as well. So that's a good illustration of the point I made earlier. Again, the triple glazed technology, we're seeing this again now more and more. What's really a key sort of visual of these high performance windows is it used to be that if you went to look into the glazing, you would typically see like an aluminium rail separating the in double glazing anyway, the two panes of glass. Now, if you're really looking to sort of have a trained eye, what you'll notice in the high performance windows is that it's a black rubberized spacer between the glass more and more. And that's a sure sign that you've got a high performance window there. And you can see in the diagram where I'm talking about that, just at the green at the very bottom, you'll see the polyurethane separators between the glass. And where this manifests itself typically is when you open the curtains in the morning, and you'll see a little bit of condensation across, particularly this time of year, at the bottom of the glass. That's because not only is there a thermal bridge perhaps from the window frame to the building, but there's also a thermal bridge from the glass to the frame, and that's typically where you get that little level of condensation. And that condensation will occur if the surface temperature is below 12 typically. So again, a little bit of the science, but I don't want to go too heavy on it. And another thing that's just going on as well with the windows before I go away from it is that there's various coatings in the glass, and what's good now is we have parameters called the G value, which will tell us how the glass will perform and how much solar light it will let in and how much heat it can take off the building. So it is actually possible on some very sophisticated buildings to have maybe different standards for the glass on different sides or orientations of the building. If you a lot of south facing glazing, it might be worth lowering or changing the G value accordingly so that you don't end up with a lot of heat coming into the room. So that's interesting as well. And again, on the north side, you can do that as well. So here's an illustration of the typical points in the building where we have, infiltration happening or indeed exfiltration because there's penetrations in the building. And when looking at air tightness, there's once you have a bit of experience with it, it's quite simple to combat really. But what I would say, when presenting about this is that, if you don't have mechanical ventilation, which we say in the industry, controlled ventilation, then your other strategy away from that, without air tightness and mechanical ventilation, is honestly, probably the best way to describe it is random ventilation. It depends on how exposed your house is. Is it on top of a hill exposed, or is it down in a hollow with loads of trees around it? A lot of variable factors will affect how well your house is insulated. And one of the things that's commonly said, with these MVHR systems, you might get something in the region of 10 to 14 complete air changes of all the air in your house in one day. Whereas if your house is naturally ventilated, you might be lucky to get 3. Depending again on a host of variables. So it's a much healthier house, and I understand for some how this can be, it almost sounds like a contradiction, air tightness and all of that, and then some of the thoughts that go with that. But again, we can pick that up in the discussion afterwards. We'll just wait for the animation to move here on this. Yeah. Okay. So yeah, it's just breaking down here in this the different percentages that you would get of leakage from various areas. So we've done many blower door tests here with our work in the college, and the whole concept of that is around, you know, demonstrating a lot of what goes on, or fire testing in houses. So I'll just go through these here and toggle through them. Again, electrical outlets, fans and vents will lead to a certain proportion of leakage as well. A fireplace, oh goodness, if you have an open fire with the chimney opened outside, it's a huge energy loss on the building. That was how stoves came to prominence. The rule of thumb is if you have an open fire, you get 30% of the heat and 70% goes out the window, where if you have a stove, you're getting 70% of the heat and you know, you're losing 30%. So that explains a bit about the phenomenon that we've seen in different you know, rural housing and domestic housing in Ireland. So again, just looking at the ventilation here, it shows the different ventilation systems that there are in the market. You've got natural ventilation with intermittent fans. This sort of consolidates what I was saying. Then you've got mechanical extract ventilation, and then you've got balanced mechanical with heat recovery. And here you can see in this matrix that we've designed exactly how each of those perform with respect to what's going across the top. And again, when looking at the recording, you'll be able to digest that in your own time. I've already talked about some of it here as well. So here's the dreaded videos. I hope this plays. Yeah, okay, so this is good. So we have a wee video here. I'll play this, and it's just giving an overview of MVHR, and then I can come back in afterwards. Okay. Okay, I can do a talk over then. There is the subtitle at the bottom, so it's just sort of explaining maybe what I'd spoken about earlier. You have the unit itself located typically in a utility room, or indeed a dedicated plant room, and the whole aim there is to make the ducting as short as possible to the unit from the intake and also from where you're exhausting it. And here we can see, you know, the fresh air being pulled in and going through the heat exchanger and getting filtered, and at the very same time the extract air getting pulled from various rooms and again going through the heat exchanger and being exhausted to outside, and again that gets filtered on the other side of the MVHR unit, or of the heat exchanger unit itself. So to go on that, yeah. Okay. So these little videos are here as well, again for everyone afterwards. Yeah, so again, this is typically what it looks like in diagrammatic form, and then there you can see as well some of the rigid spiral ducting that you can get. Now again, this isn't a seminar on mechanical ventilation, but there is others where you can get that sort of like anybody from a farming background will know it almost looks like the drainage pipes that you would put in the ground, but it's very flexible, and you can get it to bend around corners and different things. So that's the other product that's commonly used as well. And again, the criteria is already there. It has to be better than 75% efficient. Most of them on the market anyway are 90% or thereabouts, and they use very, very low electricity. Sorry, the screen is going off. Yeah. Contact me. So again, very, very low electricity demand as well, which is common. And again, the comfort criteria. So again, just talking more about it, when these units are about 90% efficient or thereabouts, it means that they will at least bring in the air, at the very least, even on the worst day of the year, even -10 outside, it will still heat the air to at least 16.5 degrees. So the comfort criteria is very much maintained. And again, they're a very, very simple technology in that they've only 3 operating speeds: 70% if you're on your holidays, 100% which is normal, and then 130% which is known as boost if you've got a large occupancy, maybe a party or Christmas dinner and things like this. And the units themselves have to comply with low decibel levels as well. So that's one of the things as well. And again, the filters I talked about, you've got an F7 and a G4 filter typically in most units, and again, we can even up those filters if needed, or if there was a particular requirement in the house, to F9, and that doesn't really affect the performance of the unit at all either. And then the other thing to say, and it doesn't really apply to us so much in Ireland at the moment, they have frost protection as well. So that means that they can, you know, if the outside temperature got really, really low, they're able to switch on a frost protection, which protects the heat exchanger as well on the incoming air. So again, another one of the systems that's out there at the moment is demand control. And again, if you're not going for MVHR, this is another system that's quite good as well. Demand control ventilation, and it's very, very popular actually in Dublin at the moment as well. So it will, as it says there, it's demand control. So it will click on depending on various metrics and ventilate the room accordingly. And then if the required metric has dipped or there's no need for the ventilation, it tempers down as well. So it's quite good. So just going back to the CO2 that I talked about earlier on at the start, you can see here that you know, if or as we go up in the various levels of CO2, you'll see that it's really quite harmful, or will affect your mood or your performance. You know, if it's a cognitive function, that's why a lot has been made about CO2 levels in education settings. In Scotland, the CO2 monitoring of classrooms has been around for years, because there was papers and research that said that, you know, cognitive function in high CO2 sort of decreases, and concentration levels, of course, as well. So that's it. Again, anecdotally, you know, where you would commonly, you know, maybe feel this, and some people mistake it with travel sickness, would be if you're in a confined space with 3 or 4 people, maybe like in a car on a long journey. You might feel a bit groggy when you get out, and that would very typically be as a result of being in a high CO2 concentration for a significant period of time, and then your symptoms would alleviate quite shortly afterwards. Yeah, another thing as well, which is just around the indoor air quality, which is my own specialism as well, might be what you would experience around relative humidity, and also, you know, the amount of ventilation that's delivered to a room. So these units that we're talking about, be it demand controlled or MVHR, deliver air at quite a low level to the room. You know, it's not like you're not going to get sucked up into one, or it's not going to, you know, give you a draft feeling in the back of your head. And God knows I have no hair, so I feel every draft there is. But again, on the antidotal thing, to sort of maybe, you know, consolidate what we're discussing here, make it a bit more real, is sometimes you'll maybe have stayed in a hotel, and it could be a very, very large centralized system, or an air conditioning unit also in the room, and you might the next morning feel like you have a runny nose, or have like a dry patch in your throat, or a little bit of a, you know, raspy throat for the morning, and that would be that the room has been over ventilated. And again, this phenomenon would be well associated with hotels. And the other place that you would experience that, and again, a lot of people think it's from, I can't rule it all out, but also in an airplane, there's a large amount of overventilation in an airplane for obvious reasons. So again, the air there can become overventilated, which means it's a bit drier, and again, that could lead to you feeling a little bit different after the flight. Not so much necessarily maybe contamination from other people on the flight. But in Ireland, it's quite stable. We're between 70 and 30 relative humidity all of the time. In other parts of the world, it's much more of a consideration. Okay, so we're switching now into, you know, just looking at some of the other byproducts that could also be in the air, and to a much lesser degree. Although the research is really ramping up around this as well, about what other nasties we can have in the house, and one of them is VOCs, or volatile organic compounds. And I think I've seen somebody from Ecological here on the call. We're really fortunate that we actually have that company here as well, Ecological Building Systems in Athboy, because they're market leaders with respect to natural materials. And I suppose going back further, you know, the construction industry has had issues in the past with, you know, new products that then years later turn out to be maybe, you know, not as good as once heralded. So it's really important that we make the, you know, informed decisions, let's say around the material selections of buildings, because it could quite easily affect the indoor air quality. But again, have a bit of comfort in that if you have an MVHR, it does, as we talked about, change the air quite a bit. So again, you're getting rid of a lot of those contaminants in the house. And then we're talking about the, you know, the comparison of buildings and NZEB. And again, I've alluded to this already quite early on in the presentation, maybe it was ahead of time with it. But the NZEB standard and passive house are quite interlinked. And again, if you're going for a quality near zero energy building or NZEB, then passive house is an excellent vehicle in which to do that. Another thing that I think is worth highlighting is that under the passive house banner, there's actually 5 standards, and there's one that I think is particularly relevant as well to the Irish market, which might help with the quality assurance thing as well. So the Passive House Institute have a low energy building standard, which is just below passive house classic, as we call it. So that means your air tightness standard that you're aiming for is relaxed, and also your 15 kilowatt hours is relaxed to 25 kilowatt hours. And with that, it's a little bit easier to achieve, but again, it has that quality framework around it, and it would ultimately mean that you would get an NZEB building as a result as well. Some of the other things about air tightness that are important to pick up maybe are the house bees much quieter, airborne sound doesn't penetrate it, and in London in particular, some boroughs have employed the passive house standard for this reason alone, which is quite interesting. But also it's a fast and assured way of protecting also your building fabric from interstitial condensation as well, when done correctly. And of course the heating demand. Here's an example of this. If there was let's say an unintended, you know, hole in your airtight layer, you're into the whole realm of interstitial condensation and having problems. So the dew point of it might be in the wall, and with that you get that condensation occurrence and potentially some structural damage or fabric damage as time goes on. So here's some stuff, a video on air tightness. I'm just conscious of time. I can leave these over so that we can pick up on them later. My own research for the PhD was in radon. So again, I was examining over 100 passive house buildings here in Ireland to see was radon better or worse in them compared to normal building stock, and was pleasantly surprised by the results. So again, you're talking about a 50% reduction in the presence of radon in one of these certified passive house buildings or a low energy home. And again, this is just reiterating the thermal bridge phenomenon that we talked about earlier in this slide. And again, really, I think we're sort of rounding out here, and I've said some of these things throughout the presentation, but again, you can pick them up in the slides. The real approach, and the one that's sure to deliver, is if you go with this fabric first approach to building, you know, the energy efficiency being the first renewable, you can always bolt on the PV panels. We can always go with the heat pump. We can always do these things as bolt-on measures later. And remember as well, all these technologies are improving all the time, and their price point will also, you know, hopefully come down as the technologies mature. So I mean, if budget was an issue, I think, you know, putting money into your fabric first is a really good approach to getting a good building. So again, yeah, that is what we've employed and embraced throughout the project, the Housing 4.0 project, and all of the various pilots, be it in Germany, over in Belgium, or here in Ireland. It's been about that as well. They've all been assessed through the PHPP modelling for passive house. So that's the presentation, but I'm really hoping for some healthy discussion, and I think as well there's some very relevant people as well in the calls. So should be good. Look forward to it.
Great, Barry. Thank you very much indeed. We've got a few questions. Just before we move on to those, it's just an opportunity for me to show my ignorance. It's when we're talking about carbon, about parts per million in CO2 levels being above 400, I never actually consider what they are within the house. What everybody is focused on what they are because of emissions outside. But you highlighted that they're way over 400 within a house before we even start, because outside the window, they're probably running at 450 or 500. And it's just, if you start at the wrong starting point, things are not going to get better.
Yeah, can I just add something there that's quite useful, maybe to just say it. So, and you can follow this maybe when I get up and going with it. But I'm about to undertake my own house to retrofit it to the Enerfit standard, and it's a 1970s bungalow. But what I did do, and it's really been interesting for me, maybe it's a bit geeky, but I have been monitoring the house for the last 4 months, and it's just a normal operating mode. So there's a stove in our sitting room, there's a kitchen, it used to be a garage, which is quite cold, and then there's one of the bedrooms. The average CO2 for the house is above 1,000, for example, and in the room with the stove. So again, because the winter season, we're out with 3 kids at home. When we come home, we light the stove, and until bedtime, that room will go easily to 1,500, 1,600 CO2 parts per million, and then it takes about 8 to 9 hours for it to fall back to maybe something like 800. So